Hello, today we're going to start Chapter 16. You probably noticed in the syllabus our first lecture is on Section 16.2. We're going to touch on a couple topics from 16.1, but after looking at it and really thinking about it, I don't think that there's any reason why you need to be doing homework in 16.1. So today we're going to start our discussion on multiple integrals and go on to Section 16.2 that deals with iterated integrals. What I want to do first of all is I want to go back to your Calculus 1 days and remember when we first defined the definite integral, we wanted to find the area under a curve. And here's my, if you can't see it too well, maybe I could have made that red a little bit bolder. But here's my curve right here that I want to find the area under that curve. And if you had me for Calculus 1, what we did was we partitioned your interval that you wanted to find the area under the curve. You partitioned it into n sub-intervals. And then what we said is you could pick any point on each sub-interval and make the height of your rectangle be the y-coordinate of that point. And in this particular case, I programmed the computer to take the midpoints. And so this first rectangle right here, the height of the rectangle was the y-coordinate at that point, and we did it for each of them. And then what you did was, if you notice, if you take any one particular rectangle, its width is delta x, and its height is my f-coordinate at that point, which we'll call fx sub I star. So for the first interval, it would be x sub 1 star, the second interval, f of x sub 2 star, whatever. And so if you take your height times your width, that would give you the area of this one rectangle. And then what you did was you summed up, okay, you summed up as I went from 1 to n. And this should be an n here. It looks like an h. It's the limit as n goes to infinity. Of I goes from 1 to n of f of xi times delta x. But the whole idea was, what did you do? To find the area under the curve, you drew perpendicular strips perpendicular to the x-axis, and you estimated the area under the curve for each of those strips by using a rectangle. And as delta x got smaller and smaller, your approximation got better and better. All right, now today what we want to do is we have a surface. Some surface, and this surface's function is z equals f of xy. So I've got some surface in three-dimensional space, and before we took a curve, and our little platform was some interval on the x-axis. And what we did was we drew perpendiculars coming up from this interval, from x equals a to x equals b. And think of this as your rooftop. And before, we wanted to estimate, or we wanted to find out exactly what was the area underneath the curve. So you had a little interval, and you took perpendiculars up from each of your end points of your interval. Well, now what we're going to do in 3 dimensions is I'm going to have some region R, and I picked this little area right here, where it's going from 0 to some particular value for your x, and 0 to some particular value of your y. And here's my region that I have in the gray. And think of perpendiculars coming up from each of the endpoints of that rectangle. And you actually could think of perpendiculars coming up along this edge, along this edge, along this edge, along this edge. And what we actually want to do is think of this as a tent, okay? A tent. And the sides along the rectangles going perpendicular up are your sides of your tent. And your rooftop is the surface. And we want to come up with some way that we can find the volume underneath the tent. You with me? The volume underneath the tent. So what I did is, if you look at this picture, in fact, let me redraw my base. My base is something in the xy plane, okay? Some rectangle, and I picked a rectangle that had one of its vertices being at the origin. And what I did was, I thought of it breaking it up sort of like with press-on tiles. All right? And these are my little press-on tiles, and your rooftop is coming up over the top. You with me? And we want to estimate the volume underneath that tent. Well, what I did was I picked one particular little tile. All right? And notice I brought up perpendiculars from each of these points. By the way, I did this all on Maple, and you people are going to learn how to do it also on Maple. And what I want to do is I want to estimate what is the volume of that one little region. Well, we're going to do the exact same thing like we did in Calculus 1. We're going to say, oh, if you have a little rectangular solid, see, let me draw it again. I need, and then I need another one just like it down here, but I should have made it dotted. And we'll have this come down like this come down like this come down like this, and this come down like that. There's a little rectangular solid. It has a width, which I'll call delta y. It has a depth, which I'll call delta x. And it has a height, which I'm not going to call delta because it's not big, it's tall, all right? So which I'm going to call, let's say, z. And my area is going to be equal my length times my width times my height, which would be delta y times delta x times z, which is my height, which I could write as z times delta x times delta y. Now, what am I going to use for my height here in this picture right here? I'm going to pick some point in that little region, and I'm going to come straight up and say, what's my height at that point, at that x sub I star comma y sub I star? And the volume of just the part of the tent that's over that one press-on tile is my height, which is f of x I star y sub I star times delta x times delta y. And we're going to do that for each of these little regions, all of them. And what we're going to have to do is sum them all up. Now, how are you going to do it systematically? Well, notice you could pick y to be constant. You could let y to be constant, and you could add up this row, add up this row, add up this row, add up this row. And after you add up each of your columns coming this way, then you can add all of them coming over that way. And so that's what this is representing here. It's saying, like, if you pick your j to be constant, let some y be constant, and look at all the ones as you let I change, the first one, the second one, the third one, the fourth one. Add up that volume. And then after that, you add up all your volumes going this way. After you have your sum of your volumes, sum them all up that way, and you're going to be summing up j equals 1 to m. So the whole idea is very similar to what we did in Calculus 1, but now we're breaking up our regions into little areas delta A, which you could represent as delta x times delta y, and then pick some point in that little region, go straight up and say, what's the height of the function at that point? And for the part of the tent that's over this one little delta A area, its volume we can write as f of xi star yi star times delta A. That's the whole idea. Okay? That's the whole idea. And notice, for each of these little delta A's, we're going to find the volume that's above us. We could pick, like this is going to be the first one, the second one, the third one, the fourth one, the fifth one. So notice this point right here would be x1 comma y1 with their little stars on it. The point you hit here would be x2 y1 star, because you see it's the second row, first column. You with me? And go across. And if you sum all those up, you can sum them up going this way. You could sum them going this way, this way. Keep x constant and let y vary, and then sum them across this way. Or you could sum them across this way and then add them up. Or if you wanted to be real tedious, you could just add each one separately. And in the section 16.1, they have you do that. But you think here, if I have you do this and it's 5 by 5, you've got 25 little estimates to do. You'd be sitting there for an hour and a half doing one problem, getting a little bit frustrated. But notice, as we sum these up, okay, we could keep y constant, one y constant, and sum this way first. If y is constant and I let my delta x's go to 0, back in Calc 1, what does this become? This becomes an integral, doesn't it? As delta x goes to 0, this becomes the integral of f of xy dx, right? And then after we sum each of those up, as we let the delta x go to 0, if we put this in here, this becomes another integral. And this is exactly what we're going to learn how to do today, which is called an iterated integral. All right? So, first of all, what I want us to do is practice. How do you do an iterated integral like this? All right? Now, before we practice, I want you to have a sense what this thing is saying. This particular one that I'm doing right here is saying y is ranging from y equals 1 to y equals 2. Notice I have dy on the inside, and so this first limits of integration is saying y is ranging from 1 to 2. All right, what is x ranging from? x is ranging from 0 to 3. Notice, what is the surface, underneath the tent on the floor? If I wanted to draw it, notice y is ranging from 1 to 2. Y is going from 1 to 2, this region right in here. And x is ranging from 0 to 3. And so my region that my floor for my tent is here. Because you have your x's going from 0 to 3, but your y's have to be between 1 and 2. Now, first of all, not even thinking about what the surface of the tent looks like, we're going to practice how do you evaluate an integral like this. You work from the inside out. All right, to evaluate an iterated integral, and most of your homework is just practicing doing iterated integrals, we have to figure out what the inside, notice this is going from 0 to 3, and then from 1 to 2 of x squared y dy dx. I just sort of spread it out a little bit more. What we need to do first of all is work from the inside out. We have to evaluate this. Now notice, y is allowed to vary in this integration that I have. Think of x as being fixed. It's very similar to partial derivatives like we did before. Okay? All right, so I'm going to evaluate what's the integral from 1 to 2 of x squared y dy. Think of x as being fixed. X is a constant. So if x is a constant, this is a constant times y. If I'm integrating 5 times y, what would I do? I'd go 5 times y squared over 2, wouldn't I? Because that's your constant. And notice this is as y changes from 1 to y changes to 2. How do I know that? Because I'm integrating with respect to y. So y is changing from, and I like to write this as y is changing from 1 to 2. And then what I need to do now is plug in y equals 2. So I have x squared times 2 squared, which is 4 over 2, minus plug in y equals 1, x squared times 1 squared over 2. And this gives me 2x squared minus 1/2 x squared, which is 3/2 x squared. Now I'm not finished yet. I just figured out that this inside integral is 3/2 x squared. So I plug 3/2 x squared back in for the integral that I just evaluated. So now I have to do the outside part. I have to go, what's the integral from 0 to 3? And for this inside integral, I found it to be 3/2 x squared. Now it's an old Calc 1 kind of problem. Bring down your 3/2 for the right, increase your exponent by 1, divide by the exponent. Looks to me like the 3's cancel. So I have 1/2 x cubed as x ranges from 0 to 3. Put in a 3 cubes 27, 27 times 1/2 is 27/2, pop in 0, which is good, gives me 0, and I get, for my first iterated integral, 27/2. Okay? Any questions? Let's do it again. Now they want me to go the other way. They want me to evaluate the integral from 0 to 3 and then 1 to 2 of x squared d. Is this the one that this is the one I just did. I'm sorry. We're doing this one now. We're going to go x squared y dx dy. And notice we're going from 1 to 2, integral from 0 to 3 of x squared y dx. We've got to figure out what's on the inside first and then go with respect to y. So what I'm going to do first of all is figure out what's the integral from 0 to 3 of x squared y dx. Now where students mess up, if they're going to mess up, on the limits of integration, notice the inside one is going from 0 to 3. What's ranging from 0 to 3? Before, when you did Calc 1, you just had one variable. You'd put the top number in for the variable, the bottom number in for the variable. With this one, after we do the integration, I'm putting 0 in for x and 0 in for 3. Or, I mean, 0 in for x and 3 in for x, excuse me. So now, if I'm integrating with respect to x first, remember, y is considered a constant. So this is like the integral x squared y. It's like 5 times x squared. You just bring the y along for the ride. Are we all okay with that? So we're going to increase our exponent of 2 by 1 and divide by the exponent and just bring y along for the ride because we're considering it to be a constant. The hardest part, it's like we're doing partial integration is what we're doing now. And this is as x ranges from 0 to 3. So we pop in a 3. 3 cubed is 27. So I have 27y over 3 minus putting in a 0 gives me 0. And I get 9y. Now what am I going to do with that 9y? The inside integral is 9y. So it gets plugged in right here. Because that was my inside integral. I take it out and I replace it with 9y. And now I have to figure out what's the integral from 0 to 2 of 9y dy. That's pretty easy. That's 9/2 y squared. And we go from 0 to 2. Popping in a 2 gives me 4, 9. Oh, excuse me, 1 to 2. Absolutely, thank you. 1 to 2. Popping in a 2, I get 9 times 4 over 2 minus 9/2 times 1 squared. And let's see, here, 2's cancel. So I have 9 times 2 is 18 minus 9/2, which gives me 18 is 36/2 minus 9/2 is 27/2. Okay? Now those of you that have a TI 92 calculator, it might be nice to go over how you can do this on your calculator. So let's do that for just this one. On the test, by the way, I have to see the work though, because you have to know how to do it. So turning on the calculator, okay, turning on the calculator, what I'm going to do, first of all, I don't know who had this calculator before. I'm going to hit F4 or F1, 2, 3, 4, 5, F6. And that says clear all characters and variables, and I'm going to hit enter so that it will do that. So if anybody stored x as 2 or something, I'm not going to get messed up there. Now, the inside integral is from 0 to 3 of x squared y dx as x ranges from 0 to 3. You with me? That's my inside integral there. So I'm going to go shift, shift, and the integral sign right here is above the 7. So I hit that, okay? And then my function is x squared times y. No implicit multiplication. You've got to put the times in between. So x to the second times y, comma, as x, comma, ranges from 0 to 3. I'm going to do my inner integration first, and then I have to put my parentheses and hit enter. Notice that did the inner integral, the inner integral. We got that answer is 9y, which is what we got before. So then I'm going to go shift integral. I want to pull that 9y back. So I come down here, I come up here, highlight it, hit enter, it pulls it down. And now I go comma as y ranges from 1, comma 2, close parentheses. So you go from the inside out, hit enter, and we get 27/2 like we had before. Okay, we've got to practice. Let's do a few more. Okay. Let's do this one right now. Let's integrate the function from 1 to 2 of the function e to the x over y dy, and then we're going to integrate with respect to x, varying from 1 to 2. Yes? I did. Don't worry about it. All right, so the first one that I want to do right here is I want to integrate from 0 to 1 and then from 1 to 2. Okay, so what we're going to do right here, we're going to do the inner integral first. We want to integrate from 1 to 2 of x e to the x over y dy. We're doing the inside one first. Okay, think, what's constant right now? X is constant. Well, if x is a constant and I'm doing this integral, I am more than welcome to bring my constant out front. Which I just did. And the integral, because x is a constant, you can factor out constants. So I have x e to the x times the natural log of absolute value of y as y goes from 1 to 2. Okay, and that gives me x e to the x times natural log putting in a 2 minus natural log putting in a 1. Does anybody remember what natural log of 1 is? It's 0. So this is equal to x e to the x times the natural log of 2. Now that's my inner integral. I'm going to take that and plug that in to my outer integral. So for my outer integral, now I'm doing, what's the integral? From 0 to 1 of x e to the x. Natural log of 2 is a constant, so I'm going to pop that out front, dx. You always work from the inside out, and it's just a matter of practicing. Okay, now to do this, unfortunately, this is a Calc 1 kind of problem. Okay, if it's a Calc 1, no, it's Calc 2, excuse me. It's a Calc 2 kind of problem. How do I go about doing that kind of integral? By parts, absolutely. As you recall about parts, the integral of u dv is equal to u times v minus the integral of v du. The ones that had Calc 2 last semester are at an advantage. This is by parts. How do we decide who's going to be u? What was a little trick? Lippets. L-I-P-E-T. L was logarithms, I was inverse trig, P was polynomial, E was exponential, and T was trig. Whichever function shows up first in the u dv is going to be u. Well, I don't have a logarithm. I got log 2, but that's nothing. That's just a constant, so forget that. I don't have an inverse trig function, but I do have a polynomial, which is x. So we're going to let u be x, and then my dv is what's ever left in the integrand. Well, if x is my u, my e to the x dx is my dv. So therefore, du is dx, and v is just the integral of e to the x dx, which is e to the x. Okay? So now, plugging in to what we have, the integral of u dv is equal to u times v minus the integral of v du. And you might want to just, this natural log 2, just put a little circle around it so you don't forget about it. I'll throw him in the end. I have u, which is x. So the integral of x e to the x dx is going to be u, which is x, times v, which is e to the x, minus the integral of v, which is e to the x, du, which is dx. And remember, our integral was going from 0 to 1, so we have to have this guy go from 0 to 1 and this guy go from 0 to 1. So here, plugging in a 1, I get 1 times e to the first minus 0 times e to the 0. 0 times anything is 0. Minus, and the integral of e to the x is e to the x, and we're going from 0 to 1. So I have e minus e to the first, which is e, minus e to the 0, which is 1, which looks like the e minus e plus 1, which gives me 1. And notice what we were evaluating was natural log of 2 times the integral from 0 to 1 of x e to the x dx. We just figured out that this integral was 1, so it's natural log of 2 times 1, or my final answer is natural log of 2. So yes, unfortunately, when you're doing iterated integrals, you know, we might have to remember how to do some stuff that we learned last semester. That does come back. Okay, the next one I want to look at is this one right here, which I know I skipped. We want to evaluate the integral x squared plus y squared dy dx. Okay, as y is ranging from -1 to 1, and x is ranging from 2 to 4. Okay, that's what we want to evaluate. Okay, and that one, what are we going to do first? Well, first, we're going to do the inner integral, this one. And I find it very helpful just to write it by itself. -1 to 1, x squared plus y squared dy. And think, when you're first starting to do this, x is a constant. Okay? So if x is a constant, this is like 5 plus y squared. Well, if I'm integrating x squared plus y squared dy, what's that going to be in terms of y? You guys tell me. X squared y, right, because x squared is a constant, plus 1/3 y cubed. And this is as y varies from -1 to 1, because we're integrating with respect to y. So that's what my limits of integration are changing with respect to. Okay, so we are going to now, it's real helpful to put this y equals 1 to -1 to 1. I'm popping in the top number, so I have x squared times 1 plus 1/3 times 1 minus, And popping into negative 1, x squared times a negative 1 would be minus x squared. And 1/3 times a negative 1 cubed is going to be a negative 1, so it's going to be minus 1/3. So this gives me x squared plus 1/3 plus x squared plus 1/3. So it looks like I have 2x squared plus 2/3. And unfortunately, am I finished? No. That's just the inner integral. So I've got to take that answer and plug him in into the outer guy. So now I'm going the integral from 2 to 4 of 2x squared plus 2/3 dx. And again, x is changing, so the integral of 2x squared is going to be 2x cubed over 3 plus 2/3 x, and we're going from x equals 2 to x equals 4. And I don't think you guys need to watch me plugging in 4 minus plugging in 2. You're going to end up getting 116/3. Are we okay with that, just to save ourselves a little bit of time and tedium? Okay, you're popping in a 4 minus plugging in a 2, and this is what you should get, 116/3. Everybody okay? Okay. Let's look at the next one. Oh. Now, I want to mention Fubini's theorem. Fubini's theorem says if f is continuous on the rectangle, which we're going to call region R, where x, the point x, y are all the points where x is between A and B, and y is between C and D, then it says if you want to have your tent having the rooftop be f of x, y, but the base be that rectangular region where x is ranging from A to B and y is ranging from C to D, it says you can do your integration either of these two ways. Now I want to show you a little bit where this is coming from. Because if you look at, you have a rectangular region, and the x is ranging from A to B, and the y is ranging from C to D. Your rectangular region is this. Okay? That's what it looks like. Now, if you look at it, suppose I wanted to integrate with respect to y first. If you integrate with respect to y, what's held constant? X. So if I pick an x between A and B and hold it constant, what is my y ranging from? My lowest value is C, my upper value is D. So my y is ranging from C to D. Now what you're going to be doing is you're going to be having little delta x's that you have all these little ones like this, but you're finding just one particular one where x is held constant and you're summing that up. But then when you want to sum up all these strips after you got your volume, what is your x ranging from? From A to B. Or, if you wanted to, suppose you want to instead integrate with respect to x first and then with respect to y. Well, if I integrate with respect to x first, you pick a y constant. Pick a y constant. If I pick a y constant, what are my x's ranging from? From A to B. And after I do all of these this way, and I want to sum up all those strips, what's my y ranging from? From C to D. So what Fubini's theorem says is, just make sure you can integrate in either order, but this one says y is ranging from C to D, and x is ranging from A to B. And this one says x is ranging from A to B first, and then y is ranging from C to D. Not hard theorem at all. So what we want to do right now is we want to evaluate the double integral x minus 3y squared dA, where R is the region, xy is ranging from all the points xy, where x is ranging from 0 to 2, and y is ranging from 1 to 2. So it's very, very simple. You're going to go integral of x minus 3y squared, and you guys tell me, do you want to integrate with respect to x first or with respect to y first? I don't really care. Why don't we do dx dy? Now if we do dx dy on the inner integral, what is x ranging from? From 0 to 2. And after we let x range from 0 to 2, what's y ranging from? 1 to 2. All right, and again, we have an inner integral right here which we have to figure out first. Those of you that are home, it might be a good idea for you guys just to turn the tape off and see if you can do this integration on your own first. Unfortunately, the people in the TV studio have to listen to me. Okay? But it's a good idea. You know, if you think, oh, yeah, Ms. Strocko, I know how to do it, turn me off, do the problem, and then fast forward and see if we get the answer. By the way, if you have your print-off sheet, you can see negative 12 is the answer, and you can fast forward through the whole thing. We're going to do the inner integral first, 0 to 2 of x minus 3y squared dx. So think y is a constant. And note, x is ranging from 0 to 2. Okay, so if we do this, what do we have here? X is not a constant, so I get x squared over 2. 3y squared is a constant, so it's just going to be minus 3y squared x. And we have to do that as x ranges from 0 to 2. And I love to write this, x is 0, x is 2, because otherwise you can really mess up. So if x is 2, 2 squared is 4, 4 divided by 2 is 2, minus x is 2, 2 times 3, oh, this is one minus sign, by the way. Popping in, this is 2, 2 times 3 is 6, so it's 6y squared, minus, popping in a 0, I get 0 minus 0, so that does nothing. So my inner integral is 6 minus y squared. Also, a key that you've messed up is if you have an x in here and the outer integrals with respect to y, you messed up. It's got to be totally in terms of y's, okay? So we take this, plug it into the inner integral, which was right here, and we now have the integral from 1 to 2 of 2 minus 6y squared dy. And then that one's going to be 2y minus, increase your exponent by 1, gives you y to the third. Dividing by 3 would give me a 2. And here we have to go from y equals 1 to y equals 2. Okay, and you pop in a 2 here. 2 times 2 is 4. 2 cubed is 8, minus 2 is 16, minus, parentheses, popping in a 1, 2 times 1 is 2, minus 2 times 1 is 2. These guys cancel, so we just get a negative 12. Okay? All right, let's look at another one. Oh, I chose this one because it gives students a little bit of trouble because of the trigonometry involved. All right. It's a rectangular region. X is going from 0 to pi, y is going from 0 to pi over 2. So we're integrating cosine of x plus 2y. Does not matter with the rectangular region what order you integrate with respect to. You'll find in the next section, appreciate this, because all the other ones, the other regions, it will matter in which order we do it in. But this one, it doesn't matter with rectangular regions. You want to go with respect to x or with respect to y first? Doesn't matter to me. X, okay, we'll go dx, dy. So what's x ranging from? 0 to pi. And what's y ranging from? From 0 to pi over 2. So we have to do that inner integral first. Okay, and the inner integral first is the integral from 0 to pi cosine of x plus 2y dx. And notice this is as x ranges from 0 to x ranges to pi. We're doing this guy first, which we have to. You must go from the inside out. All right, now here, how do you want to do this integral? Well, the only kind of integral I know how to do with cosine is the integral of cosine u du. And I know the integral of cosine u du is sine u. Right? As a derivative of sine is cosine. So we have to do a u substitution. Now how's my u substitution going to work? U is what's in the parentheses here, which is x plus 2y. Now notice we're integrating with respect to x, so remember, y is considered a constant. So this is just like x plus 5. So what does my du equal? My du is, if y is a constant, my du is 1 times dx, right? Du dx is 1, so du is dx, because x is your variable. So therefore, this becomes cosine u du, which is sine u. I like to make my substitution back. What's u? It's x plus 2y. And what are my limits of integration? They are as x ranges from 0 to x ranges from pi. So we're going to pop in a pi. So we have sine of x plus, oh, excuse me. Why did I mess up? x is ranging from pi to 0. So I'm plugging in pi in for x. So I have sine of pi plus 2y minus sine of 0 goes in for x. 0 plus 2y is 2y. Now you might be very happy with that, but I'm not. Okay. I want to simplify this a little bit. Do you remember? Probably not, but let's go over it anyway. Do you remember when you had sine of x plus y? Remember your sum formulas for your trig? If you don't remember them, they're in the front flap of your book under the trig section. That equals sine x cosine y plus cosine x sine y. Remember that? I think you have my book right here. I think in the multivariable guide they have the trig. Oh, they don't. Well, you have your old Calc 1 book. Your old Calc 1. Oh, they have table of integrals. Do they have your trig for you? If not, you might just have to pull out your old. No, they just have differentiation. They assume if you're in Calc 3, you know what you're doing. So get out your old Calc 1 book, and they have your formulas there. Well, taking this, look what I have here then. I have my inner integral was sine of pi plus 2y minus sine of 2y. And using my double angle formula, or my sum formula here, this is equal to sine of pi cosine of 2y plus cosine of pi sine of 2y. And then we have minus sine of 2y. Well, does anybody know what sine of pi is? It's 0. And what's cosine of pi? It's minus 1. So 0 times anything is 0, so I have minus sine of 2y minus sine of 2y, which is minus 2 sine 2y. And that was a bit painful, but it's much better to have me do the painful thing than you have to do it all on your own. So now we go back here, and we take this answer, and we plug that into our inner integral. So we have the integral from 0 to pi over 2 of minus 2 sine of 2y dy. Okay? And that one's not too painful. Can anybody integrate that for me? You can do your u substitution, but I'm thinking if I take cosine of 2y, remember when you integrate, if you differentiate this, you better get what's inside. Well, the derivative of cosine 2y is minus sine 2y times the derivative of what's inside, which is 2. Okay, so that's the integral of that. And we're going from y equals 0 to y equals pi over 2. So we have cosine of 2 times pi over 2 minus cosine of 0, which gives me cosine of pi minus cosine of 0, which is a negative 1 minus 1, which is a negative 2. Okay, so we just start to review our trig just a little bit. Okay, let me get to my next problem. Make sure I didn't pull one away. Okay, oh, this is a nice one. Before we do this one, let's review just a smidge. Okay, to review just a smidge, can anybody remember what's the integral of 1 over 1 plus x squared dx? Does anybody remember what that is? It's what? Arc tangent. The angle whose tangent is x. All right? Now this one we could integrate either way, but I'm going to integrate 1 plus x squared over 1 plus y squared. I'm going to integrate with respect to y first and then with respect to x. Notice y is going from 0 to 1 and x is going from 0 to 1. So we have to do this first. Okay? So I have to figure out what is the integral of 1 plus x squared over 1 plus y squared from 0 to 1 dy. Now let me ask you something. What's x? A constant. So since x is a constant, you can factor that constant out. Okay? What is the integral of 1 over 1 plus y? Notice 1 plus x squared is just a stinking constant, and this gives us arc tan y as y goes from 0 to 1. So we have arctan of 1 minus arctan of 0. Find me the angle whose tangent is 1. What angle between 0 and pi over 2 has its tangent equal to 1? Now the beauty of the TI-92, if you didn't know that, if you turned on your calculator and you hit inverse tan is right above the tangent key, arctan of 1 is very nice and gives it to you. Whoop, 45. What mode do you think I'm in right now? I think I'm in degree mode, so I better come down here, turn this over here, and option number 1 is radian, and hit enter on that. So if we want arctan of 1 there, that's much better. That's pi over 4. The angle whose tangent is 1 is pi over 4. So this is 1 plus x squared times pi over 4, and the angle whose tangent is 0 is 0. So we have pi over 4 times 1 plus x squared. So we're going to take that, plug it back in here, so we have the integral from 0 to 1 of pi over 4 times 1 plus x squared dx. And definitely the pi over 4 I think I'm going to factor out. And this is a Calc 1 problem. I'll do it very quickly. You don't even have to listen to me. The integral of 1 dx is x plus 1/3 x cubed. We're going from 0 to 1. You plug in a 1, you get 1 plus 1/3, which is 4/3, minus, pop in a 0, you get 0 plus 0 is 0. When you go this times this, the 4's cancel, and we get pi over 3. Nice little problem. Nice that it made us remember what the integral of 1 over 1 plus x squared dx was. That was arctan. Okay, this one. They're not asking us to evaluate it. We very well could, but they're not asking us to. They just want us to sketch the solid whose volume is given by. Now notice the base. If I draw the base has x ranging from what to what? X is ranging from 0 to 1. And y is ranging from what? From 0 to 1. If I just drew something in the xy plane, x is going from 0 to 1, y is going from 0 to 1. And we're talking about this lovely little square, x ranging from 0 to 1. Now, what does my rooftop look like? What's my rooftop? My rooftop, so my rooftop is z equals 4 minus x minus 2y. That's my rooftop, my f of xy. Well, what's that a graph of? That's a graph of x plus 2y plus z equals 4. Does that help you? What is that a graph of? It's a plane. So this is my rooftop, but the floor is that little square where x is ranging from 0 to 1 and y is ranging from 0 to 1. Now they want me to sketch this. On a test, I have no problem if you say, Mrs. Strocko, that's the base and that's my rooftop. And I understand that, but let me give it a stab at drawing it for you, okay? All right, first of all, in three-dimensional space, x, y, z. X is ranging from 0 to 1. Y is ranging from 0 to 1. Notice I have to make this side parallel to the x-axis, this side parallel to the y-axis. Now notice my rooftop is the plane z equals 4 minus x minus 2y. We have crucial points. Notice this point right here is 0, 0. This point right here, x is 0, y is 1. This point right here, x is 1, y is 0. And this point in the xy plane, x is 1, y is 1. All right, now up here, let me just make, well, if I look at 0, 0, and I want to know, oop, how high is the rooftop? You with me? If I look at 0, 0, and I say, how high is the rooftop? If I want to get z of 0, 0, I plug 0, 0 in here, 0 for x, 0 for y, and I get 4. So my rooftop at 0, 0 is 1, 2, 3, 4 units high. Okay? If I want to know where's my rooftop at 0, 1, well, I want to know what's z at 0, 1. I put a 0 in for x, a 1 in for y, I get 2. So it's going to be about 1, 2 right here. If I want to know what's z of 1, 0, 1, 0, I get minus 1, minus 0. 4 minus 1 minus 0 is 3. So that's a height of 3 there. So that's 3, so we'd be about here. And the last one, what's z of 1, 1? I get 1 minus 2, 4 minus 3 is 1. So at z 1, 1, we have a height of 1. And if I play connect the dots, can you sort of picture it? This is your rooftop, and these are your sides. And that integral is going to find that volume underneath there. Drawing is an art form. I'm not going to have you guys do too much, but it's nice to be able to picture it and see what it looks like. Okay. As you can see, this plane is your rooftop, and this is your floor. And you're finding the volume underneath that rooftop of that tent. Okay. In this one, I'm a little upset with the textbook because they should say all the surfaces in this region that we're giving you will be above the XY plane. They should have a little disclaimer there, because at this point, just assume that they all are, because they all are. In later sections, we're going to be having to worry about, just like in Calculus 1, when your function went below the x-axis and all of a sudden you got negative areas. When your surface goes below the XY plane, you're going to get negative volumes, right? In this section, we're not doing that. So all your surfaces are going to be above the XY plane. Now this one sounds like it's very difficult, but it's not, and let's just talk about it. It says find the volume of the solid that lies under the hyperbolic paraboloid z equals 4 plus x squared minus y squared. I just took the liberty of going into Maple and telling it to graph that function, that surface for us. And when I told it to graph it, I limited it for x to range between -1 and 1, and y to range between 0 and 2. And what we've been doing for the last 45 minutes is we said that if you take the integral of f of xy, and I don't care if you go dx dy or dy dx, if your surface is above the xy plane, what this integral will give you is the volume of that tent that has this for its rooftop and its base here. Notice this is the z-axis, this is the x-axis, and this is the y-axis. And this little region that I have here shaded, x is ranging from -1 to 1, and y is ranging from 0 to 2. So the integral that we need to set up is going to be integral. What's my f of xy? It's what z equals. 4 plus x squared minus y squared dx dy. And then we have to say, what is x ranging from? From -1 to 1. And what's y ranging from? From 0 to 2. And please notice something. With this double integral, notice you're going sum, f of xy times delta x times delta y. What do these f of xy, delta x, delta y's represent? They're representing those little rectangular solids, right? Height times width times length is what they're doing, and you're summing them all up. If you partition this into a whole bunch of little tiny pieces. You with me? Okay, now, since you guys are getting tired and you've watched me do about 25 of these integrals already, let's do this on the calculator. Okay, so if I pop this on, because this one's pretty easy. Putting it on the calculator, all right, first turn it on, that would be helpful. I'm going to hit F18 and then clear to get rid of everything. My inner integral, I'm going to go Shift and then number 7 for integral. What I'm integrating is 4 plus x squared minus y squared, comma, as x ranges from, x is ranging from -1 to 1. -1, comma, 1, close parentheses. And I got all my commas in there. That's doing my inner integral. And the TI-92 is nice, you know, if you do it by paper and pencil, it's sort of nice to be able to check yourself as you go. I hit enter. Notice that answer is totally in terms of y's, because I'm going to take that now, that solution, and I'm going to integrate from 0 to 2 of whatever I got with respect to y. In this case, I'm integrating, my answer was a -2 times 3y squared minus 13 all over 3 dy, as y ranged from 0 to 2. And on the TI-92, what's so nice is I can just go Shift Integral. I can use my little arrow key here to pull that back up, highlight it, and then just hit enter to pull it down. And I can say comma as y ranges from 0 to 2, close parentheses, hit enter. And I just got a 12, is what I got. I just got a 12, which is the right answer, which is good. Okay? Okay, we got another one. Oop, I marked it. Find the volume of the solid enclosed by the surface z equals 1 plus e to the x sine y, and the planes x equals plus or minus 1, y equals 0, y equals pi, and z equals 0. Now let's just talk for a second. I'm just going to look at R2, my base. This is my x-axis, this is my y-axis. If they say x is ranging from minus 1 to plus 1, x is ranging from minus 1 to plus 1, y is ranging from 0 to pi. Do you see the rectangular region they're talking about? This one right here. X is ranging, any point, x is ranging from -1 to 1, y is ranging from 0 to pi. Now, what is this z equals 0 that they're giving us? Notice, where is z equals 0? What is that? That's the xy plane. That's the xy plane. Z equals 0, all the points that have z equals 0 are the points on the xy plane. Now notice, they're taking x ranging from 1 to -1, and y is ranging from 0, let's say, to pi. And our rooftop, or our base, is right here. Do you see that? That's what our rooftop is, because we have x going from -1 to 1 and y going from 0 to pi. Now this surface is going to be our rooftop, and I don't know what that surface looks like. It looks something like this, let's pretend, okay? And what is z equals 0? Z equals 0 is the bottom. Okay, and then x equals -1 is this. Now what I've done is I took the time to program Maple to actually graph this for us. So let's put it onto Maple. Just have to wait till the computer warms up real quick. Of course, I spoke so long that it's going to lock. Okay, there you go. All right, now let's go back to this picture right here, and let's go up here. And this is that surface right here. This is what I was talking about 2 minutes ago. And by the way, you guys are going to learn how to get Maple to do this also. Now the beauty of this is, notice x was ranging from -1 to 1. Right here is the origin, 0, 0, 0. This is my x-axis. And I have x ranging from -1 to 1. Y is going from 0 to pi. So this is my base. They say the bottom is z equals 0. And here's my rooftop. Now what's nice about when you do it in Maple, though, if you look, if I click on this graph, okay, notice up here, now right now, for some reason there should be little arrows here. Sometimes when your memory's getting a little bit low, they don't have little arrows for changing your angles. But notice, if I highlight up here, right now my angle is 55. If I put 60 and then hit enter, notice I can get different views here. I can come over here, and instead of at 26, I can put 30. If your memory's not too low, you get little arrows, but you can just hit those little arrows to rotate your graph. So let me just let this be 32. And I think most of you can see this is your rooftop, this is your base, and you're thinking of perpendicular lines, perpendicular planes coming up from the xy plane of your sides, and you want to find the volume of that underneath. Now we're going to do this one just because it has an e to the x in it, and I think that'll be a good thing for us to look at. So you guys tell me. Well, in fact, let's see if we can draw it right here. If I draw my base, notice, what does my base look like? We have x ranging from -1 to 1, and y is ranging from 0 to pi. So this is what your rectangular base looks like. Okay, and so my volume is going to be the double integral of 1 plus e to the x sine y. And we could go with respect to x, and then with respect to y, or with respect to y, and then with respect to x. This one, what is x ranging from? If you fix y, and you take an arbitrary y, but fix it, and look to see what x is ranging from. X is ranging from -1 to 1. And then if I sum all those up, what are the y's ranging from? From 0 to pi. And as always, we need to do this inner integral first. So the first one that we want to do is we want to do the integral from -1 to 1 of 1 plus e to the x sine y dx. And remember, this is as x ranges from -1. X ranges to 1 by that. And put that down, because if you're going to mess up, you're going to end up plugging in a 1 and a -1 in for y. Now remember, y is a constant. So if I integrate 1 with respect to x, what do I get? X. Sine y is a constant. So if I integrate e to the x, I just get e to the x, and sine y comes along for the ride, and we're plugging in -1 and 1 in for x. So plugging in 1, I get 1 plus e to the first sine y minus -1 plus e to the -1 sine y, which gives me 1 plus e sine y plus 1, because it's minus a minus, minus e to the -1 sine y, which gives me 2 plus e to the first sine y minus, and instead of writing e to the -1, do you mind if I write it as 1 over e sine y, because that negative exponent gives me troubles. And that's my inner integral. Now taking that, we got to now plug that in, which I just had, and let me put it here so we can copy it. My inner integral was 2 plus e times sine y minus 1 over e sine y dy. And notice, this answer better not have any x's in it. If you did, you messed up. It's got to be totally in terms of y to integrate with respect to y. Now, integrating with respect to y, the integral of 2 is 2y. And notice this is y going from 0 to y going to pi. Let's see. E is a constant, and the integral of sine y is minus cosine y. Right? Because the derivative of cosine is minus sine. So this will be plus 1 over e cosine y. And we're going from y equals 0 to y equals pi. So we have 2 times pi minus e cosine pi plus 1 over e cosine pi minus 2 times 0 is 0 minus e cosine 0 plus 1 over e cosine 0. Now let's see, what's cosine of pi? A -1. And cosine of 0 is 1. So finally this gives me 2 pi minus times a negative is plus e minus 1 over e minus e plus 1 over e. So that gives me 2 pi e plus e is 2e minus 1 over e minus 1 over e is minus 2 over e is my final answer. Okay? And one more to look at. This one, I took the liberty of putting it on Maple, but I want to talk about it before we actually look at it at Maple. This one, the actual integration is a piece of cake. It's not too hard at all to do, so I don't even know if we're going to bother doing it. But let's talk about setting it up. Find the volume of the solid in the first octant. What's the first octant? That's, if you think about the x, y, and z, the xy plane, the xz plane, and the yz plane, if you think about them, they're breaking up three-dimensional space into 8 regions, right? You follow the 8 regions? Are you with me? If you think of him coming back, think of the xy plane. This comes back here. R3, here's the xy plane. You have 4 regions, 1, 2, 3, 4. You follow because you got your walls coming down like this. And then below the xy plane, you got 4 more. Well, the one in this corner right here, where x, y, and z are all positive, is called the first octant. Mathematicians do not give any of the other octants names. Just the one where everything's positive is called the first octant. You don't have one where x is positive, y is negative, and z is negative. You would go nuts if you did that, okay? So just the first octant. So they're talking about the part, you have this cylinder, z equals 9 minus y squared, and the plane x equals 2, and you want to know what's the volume of that solid. Well, increasingly in this section, we're going to have to start drawing these pictures. So let's draw this one freehand first. First of all, let's draw z equals 9 minus y squared. Well, what if I have, this is my z-axis, and this is my y-axis? What does the graph z equals 9 minus y squared look like? It's a parabola, right? Is he an up z or a down z? He's a down z. How high does he go? Well, when y is 0, z is 9. He's going to be going like this. Okay? Now, when you have an equation that's missing one of your letters, in the first chapter that we did in this course, we learned, draw it just in the yz plane and then drag it along the x-axis. Now, since we're only dealing with the first octant, I'm not going to draw this all the way. Normally he goes like this. Z equals 9 minus y squared is going to be going like this and then down. Since we're only interested in the points in the first octant, I'm just going to draw this part. You with me? And now let's drag him along the x-axis. And what I'd like to do is I just like to draw a new axis and then just parallel him. And bring your parallels like this. You see it? You see in the first octant, this is your roof. It's sort of like, those people that buy, they get sunrooms or something. They have those cute little curvy roofs, Here's my floor. But now they say, Miss Strocko, chop it off on the plane x equals 2. Well, why don't I make x equals 2 right here? So here's my x equals 2. Now you can see I have this lovely floor. There's my floor, except I don't know what the y-coordinate is right there. Can anybody tell me what the y-coordinate is? At this point right here, can you tell me anything about the z-coordinate? z0, aha. So if you have z equals 9 minus y squared, if z is 0, you get y squared is 9, or y is plus or minus 3. So that baby cakes right there is y is 3. And this is x is 2. So look at that beautiful rectangle I got. X is ranging from 0 to 2. Definitely my picture's not drawn to scale, but you can live with it. And y is ranging from 0 to 3. And what's my roof? My roof is 9 minus y squared. So what's my integral going to be? My roof is 9 minus y squared. You want to integrate with respect to y first and then with respect to x? Or let's do that one first. dy dx. What's y ranging from? 0 to 3. What's x ranging from? 0 to 2. For those of you that do not have TI 92 calculators, if you're at the campus or if you spent the money to buy Maple, let me come down here, make this nice and big. Oh, by the way, here on Maple, as you can see it, there's the picture. Here's that lovely surface right there. Okay, and I wanted to turn him a little bit. Oh, I want to do it the other way. You can see you've got that lovely little region there. Here's your floor. There's your rooftop. And here x is ranging from 0 to 2 and y is ranging from 0 to 3. But coming down here, let me make this nice and big. We're going to do this problem that I just had. Hopefully you had that copied. All right, so my integral is 9 minus y squared. So I just type INT. What am I integrating for my inner integral? 9 minus y squared. 9 minus y raised to the second power as, comma, y equals in Maple. Oops, if I did caps, which I don't want. Y equals, and what's y ranging from? 0, dot, dot, 3. In Maple, you go 0, dot, dot. Close parentheses, and then a semicolon. I'm doing the inner integral. The integral, and notice on Maple, if you come up here and you hit the little maple leaf, get rid of it. Is that pretty print? Aha, there it is in pretty print. 9, integral from 0 to 3, 9 minus y squared dy. Okay, and if I hit enter on that, you don't have to do it on pretty print. I get 18. So my inner integral turned out to be 18. Now I'm integrating from 0 to 2 of 18 dx. Sort of overkill to use Maple, but let's do it. I can type INT parentheses. Now, to bring down the previous entry, we could type 18, but if I type percent, like what if my inner integral was 3y cubed to the 24th minus sine of y plus e to the 2y cubed or something. Percent brings down the previous entry, comma, as x goes from 0 to 2. Close parentheses, semicolon, and my final answer is 36, which is what we should have. So we just evaluate that at 36. This would be a simple integral for you to practice on. You really didn't need to see me do it. All right, now what you people need to do is on pages 1025 to 1030, look over the examples. Very nice examples. Look at them. And then on pages 1030 to 1031, you need to know how to do 1 through 29, the odds. All right, and I'll see you people next time.